So today we're starting with taking a look at converting between logarithmic and exponential form, following up on yesterday's work. The first one is fairly simple and straightforward compared to yesterday's. There's not a new wrinkle in that yet, like we're going to be getting here in a little bit. So in order to change that from logarithm form into exponential, it means I'm going to be writing it like this. In order to write it like that, then the first thing I write in there is the b value. Notice where b comes from in the logarithm. It's the base. It's the number that's written smaller and lower. So in the case of our first problem here, what is the value of b? 2, yeah. All right, so next thing I write in my exponential form is x, which is in the exponent. Notice where x comes from. It's what the logarithm is set equal to, the number that's by itself. So in this case, what number is the log set equal to? 5. 5 is the one that's by itself here. So it's 2 to the power of 5 equals, process of elimination would tell you what it is, but if you're not sure, you could always go back up here. You could say, hey, it's the y. That's the big number that's in the logarithm, and so it is the 32. So our first one ends up being 2 to the 5th equals 32, which really, when we take a look at those numbers, it's a good thing that's how it got organized, because that's the only way that is a true statement. It's the only way we could rearrange those three numbers in an exponential to make it true. All right, second one now. I need to turn this one into an exponential form, so again, I'm doing the same process. The first thing I put in there is that b value. That's the base. What's the base on the second problem here? Yeah, it's 5. And now the exponent. Log always equals the exponent. So what does it equal in this case? What's it equal, guys? 3. Yeah. So it ends up being 5 to the power of 3 equals, it's got to be n, right? That's the only thing that's left. So it ends up being 5 cubed equals n. But then for this third one, well, the third one is where things start getting a little interesting, because there isn't a base written there. What is going to be to the power of here? And so in order to answer that question, we know that there has to be something there. In math, we usually have something assumed to be written in. For instance, like if I just write x, remember that's really 1x. We assume the 1 is there. If I write root x, there's no number written in there, but we assume it's a 2. It's a square root. In the same way, when we deal with a logarithm, there is an assumed number there. We assume that it is going to be a 10. And so this is then going to need to go into your notes. So in your notes, please add this. Since log y equals x becomes 10 to the x equals y, that means that anytime you see log y, that's exactly the same as if I had written log base 10y. Both those statements are saying the exact same thing. This is just another way to look at that information. All right, so have that down to your notes. And now we can actually go and use that. So let's go back to that problem that we were just looking at. So I have log 100 equals 2. The first thing I need to put in my exponential form is the base. What is the base here? 10. 10, absolutely. It's going to be 10. So it's 10 to the power of what? 2. Log always equals the exponent, so it's the 2. And so 10 squared equals 100 here. Make sure you have those correct examples down on your paper so that then you can look back at it as a reference. And then the whole reason why we're learning to switch between exponential and logarithmic form is it's going to allow us to solve some problems that we couldn't otherwise solve. We can actually calculate values of logarithms. And so to see how we can start doing that before we get into the calculator type work, let's take a look at how we would figure out each of these types of problems. So first up, write down that first problem, log base 2 of 8. In order to be able to solve this and figure out what that equals, I'm going to kind of help you envision a way to think about it. So log base 2 of 8, I'm going to say that it equals x, because I'm trying to figure out what it equals. And I'm just calling it equals x here just as a way to visualize where that goes. If I then take that and write it in exponential form, it gives me a way to think about what log equals. Because if I turn that into exponential form, it becomes 2 to the power of x equals 8. So notice what log is really saying. what the log base 2 of 8 is saying is it's saying really 2 to the power of what equals 8. Because notice that's how it ends up getting written there. So then we aren't quite to the point where we're going to be needing calculators for this. So this is actually a nice pretty value that you can know off the top of your head. 2 to the power of what equals 8? Well, 2 times 2 is 4, times 2 is 8. So that's a total of 3 2's multiplied. So it is 3. So log base 2 of 8 equals 3 because 2 to the power of 3 equals 8. Okay, let's take a look at the next one. Log of 10,000. First of all, think about what it's really asking you to do. What is the base that we haven't written in? What's the base that is not written? 10. Yep. So really what this is saying is 10 to the power of what equals 10,000. And problems like this actually can be super easy once we know a little trick. So I want to show you this trick. 10 to the power of 1 is just 10. 10 to the power of 2, that is 10 squared. That's 100. 10 cubed would equal 1,000. What do you notice here?
The zeros in the exponent.
Yeah, the zeros. It's the same number of zeros as you saw in the exponent. So 10 to the power of 1, it's a 1 with 1 0. 10 cubed is a 1 with 3 zeros. So 10 to the power of what would be 10,000? 4, absolutely, because there are 4 zeros. All right. Take this idea, practice it, do the third one there on your own here. Should just take a few moments. First thing we do, of course, think about what that really means. It means 5 to the power of what equals 25. Now I'll tell you though, it's really tempting to think 5 here because we tend to think 5 times what is 25, but it's actually saying 5 to the power of what is 25. So that's why it's just 2. So it ends up being 5 squared equals 25. So our answer here is 2. Next up, we're taking a look at some fractions. So please write down that first problem. And then we're going to take a look at how to deal with these fraction operations that involve variables. So for that first one, we're multiplying fractions. The fact that there's an x in there isn't going to change the basic technique. To multiply fractions, multiply straight across the top and straight across the bottom. So in this problem then, on the top I'm going to have to do 4 times 5. 4 times 5 gives us 20. Okay. So that's 20 over. Then do the 3x times the 6. Now because we're multiplying, we can do this. And so 3 times 6 gives us 18. And so 3x times 6 gives us 18x. So we've done the multiplication, but we're not actually done with this problem because it can reduce. Always reduce your fraction. So what can I divide top and bottom by here?
2.
2. So divide top and bottom by 2. That gives us 10 over 9x. Notice the x is still in the bottom there. Okay, on to the second. Write the second problem down on your paper. And then we have to remember, how do we divide fractions? Well, dividing fractions, that's the one where we have to flip the second and change it to multiplication. So I'm going to start by taking my x over 8, keeping it exactly as it was. Then I flip the second fraction, always the second fraction. It does not matter what the numbers are or anything like that. It's always the second fraction that flips. And when I do that, I change the division to multiplication. If you like fancy terms, what we're doing is we're multiplying by the reciprocal. Now, we go ahead and multiply them. Go ahead and do that multiplication. So to do that multiplication, we go straight across the top, straight across the bottom. X times 2 gives me 2x. 8 times 1 gives me an 8. Can that one be reduced? Yes. Yes, it can. We can divide top and bottom by 2. So 2x divided by 2 gives me x. 8 divided by 2 gives me 4. Final answer is x over 4. Make sure you have that correct on your paper, and then we're going to go take a look at a different variation of these. So multiplication and division with the x in there, it wasn't too big of a deal to have the x in. But it does make it a little bit trickier when we do addition and subtraction. So go ahead and write down this first problem now, our subtraction problem. 1/6 minus x over 3. And then anytime we add or subtract, we always need to start with the same thing. What do we always need to start with? Oh, what do we always need to start with? Yeah, common denominator.
Common denominator.
The bottom has to be the same. So in this problem then, I need to make both the 6 and the 3 into the same thing. So I'm going to want to make them both into a 6 here. That's going to be the easiest. You could have been thinking also turn them into both 18. That would technically work, but you're going to have more reducing to do at the end if you do it that way. So I'm going to turn both into 6. Now, since the first one is already over 6, I just need to leave it. The second one though, what am I multiplying both the top and the bottom by? 2, absolutely. Because 3 times 2 gives us a 6. So, oops. So that gives me 2x over 6. All right, now we go ahead and do the subtraction. But this is where sometimes people get a little tripped up. So when we do addition or subtraction, we need a common denominator because that denominator stays the same. So it's still going to be over 6. But when we do the tops, we're doing 1 minus 2x. The 1 does not have an x in it, but the 2x obviously does. That means they are not like terms. That means that although we could multiply them like we did in the previous examples, we cannot add or subtract them. So it's just going to end up staying 1 minus 2x. And then that's our final answer. It cannot be reduced at all because in order for us to be able to reduce it, I would have to be able to divide the bottom and everything on the top by the same thing. Although I can divide the 2 and the 6 by the same thing, I can't divide the 1 by that. So it cannot be reduced anymore past that. Okay, now go ahead, write down the second one. And then we're going to work through that one to see what happens when the x is in the denominator. Okay, so since we're adding, again, we need a common denominator at the start. But this has an x and this has a 5. The only way we can get a common denominator here is then to turn them both into a 5x. So when there's nothing related already, multiply them by each other. That means that for the first one, the first fraction, in order to turn that x into a 5x, I got to multiply it by 5. Whatever we multiply the bottom by, we multiply the top by the same thing. So the top becomes a 15. The second one, in order to turn the 5 into a 5x, I multiply by x. So I multiply the top by x as well, so that gives me a 2x. Now that I have the common denominator, I can go ahead and do the addition. So the bottom stays the same. Remember, the bottom has to be the same, therefore it has to stay the same. That's always true. And then we add on the top. And once again, they're not like terms. The 15 does not have the x in it. And so we're just going to have to write it as 15 plus 2x. And then that's our final answer. Can't reduce it all here because, again, there's nothing I can divide 15, 2, and 5 all by in order to be able to reduce it down. All right, so having done those, I'm going to give you 2 more. I'd like you please to go ahead, write down, and figure out what each of these 2 equal. And then once you've done that, then you're going to be good to go on doing these fractions. All right, so for the first one, we need a common denominator. But one thing that I see a lot of as I walk around is people turning them both into 4. But notice that the second one here has got an x in it. So I can't just turn them both into 4. I have to turn them both into a 4x. So for the first fraction, it's going to be over 4x. The second fraction also over 4x. So that's a matter of what do we multiply by. So 4 times what gives me 4x? It's got to be an x. So I multiply top and bottom here by that x. So it's 3x over 4x now. Then, what do I multiply the 2x to get 4x? Got to be a 2, right? So then 1 times 2 gives me 2 on top. Now I can go ahead and do the addition. So it's going to be over 4x, and then we do 3x plus 2 on the top. They are not like terms, so it stays 3x plus 2. For the second one, we're dividing. Dividing fractions, remember, means flip the second and multiply. So first thing I want to do is I want to write it out where the first one stays the same. I change division to multiplication, and I flip the second fraction. Now I can go ahead and do that multiplication. Remember, multiplication happens straight across the top, straight across the bottom. So 3 times x gives me 3x. 8 times 3 gives me 24. Can that reduce?
Yes.
Yes, it can.
1x over 8.
I can divide both by 3.
1x over 8.
So we end up getting x over 8. There's our final answer.